Assalamu alaikum. It's our lecture on advanced electromagnetic field and waves, and in this lecture we are going to solve assignment number 2 of advanced EMT. Our assignment number 2 is basically to find the reflection and transmission coefficient of electromagnetic field. Okay, so let's start. To do so, we have an example like we have three regions N1, N2, and N3. Okay, electric field wave is coming from region 1 having an electric field into the x direction. Okay, you can see here your electric field is in the x direction and your wave propagation is into the z direction. This is medium 1, region 1, this is region 2, and this is region 3. Region 1, N1, N2, and N3. Your wave is coming, some of the wave goes transmitted into the N2 and some of the wave reflected back. So the wave is reflected back having the same direction of electric field in x direction, but the wave propagation direction now changes into the negative of the z direction. But how you can find the direction of magnetic field? Definitely, if electric field is in x direction, your wave propagation is in the z direction, definitely your magnetic field is in the y direction. Either this is inward or outward. You can find by the right hand rule. We already told you in my previous lectures how you can find. Okay, in this scenario, going incident wave, your this is in the positive y direction, outward, and for the case of reflecting back, your magnetic field is into the page, means minus y direction. Understood? And some of the wave is transmitted into the second medium having the same direction of electric field, E plus for incident into the second medium, because now you are in the second region. That's why I am using E2 plus. And the direction of wave propagation is now along the positive z direction. Again, now it is denoted by k2 plus, because now you are in the second region. Some of the wave is again transmitted into the region 3 and some of the wave is reflected back. So whereas the reflected back wave concerned into the region 2, it is denoted by E2 minus for the case of reflection back. And here is also the wave propagation direction now changes. Your electric field in the again in the x direction, but the direction of the wave propagation now inverses and goes into the minus z direction. Again, for the case of going wave, your magnetic field is positive y direction, and for the case of your reverse back wave, after striking the boundary, your magnetic field is in the minus y direction. Okay, and here is the boundary. First boundary is at z equals to 0 and your second boundary is at z equals to d. Now some of the wave from region 2 transmitted into the region 3 having the direction of electric field same into the x direction, having E plus t. T means transmitted, plus means going wave. Okay, and also the wave propagation direction is in the z direction, means k3 plus. While your magnetic field again in the positive y direction, because there is no again medium beyond this region 3, so there is no reflecting back wave. Okay, so how you can write their equations? Okay, so here how you can write their equations. So whereas the region 1 concerned, you have to write the electric and magnetic field equations, because you know that whenever we are concerned with the electric field, the region 1, the electric field direction is in the positive x direction, is either for going wave and either for reversing wave. Both is for the common thing is the direction of electric field, which is why that's why I am taking x cap, means direction of electric field, x cap is taking common. Whereas your incident concerned, you have to write E naught I, means incident, e power iota k1z minus omega t. I take common iota, so it becomes iota k1z. Why k1? Because you are into the first region. Okay, iota k1z minus iota omega t. Okay, plus because again your electric field direction is in the positive x direction, that's why plus here. Means E naught r means reflecting back wave, which is this is incident wave in region 1, this is reflecting wave in region 1. So E naught r, only the changes is the wave propagation direction changes, so you can see it becomes E naught minus iota k1z plus omega t. Okay, why this? Because now you are taking a minus sign with k, that's why here iota k1z, here you can see it becomes minus iota k1z. Okay, because you take minus common, that's why inside I use plus sign. Understood? Now you have to write the same equation for the case of magnetic field into the first region. You know that the magnetic field in first region is in the y direction, but for the case of incident this is positive y, for the case of reflecting back this is negative y. So taking y cap common, okay, here is the amplitude of the magnetic field, which is h naught, and you know that h naught is basically equals to E naught by z. Okay, whereas your first region, so it becomes E naught I, means for the case of incident divided by z1, because you are in the first region, e power iota k1z minus omega t as it is. Now reflecting back wave, because the direction of now magnetic field changes, and this is into the negative y direction, y is already common, so negative sign here, E naught r divided by z1, because you are in the first region. Again the wave propagation direction changes into the negative z direction, that's why negative, here you can see negative iota k1z minus iota omega t. Understood? So this is how you can write the equations of electric and magnetic field. Now move on towards region 2. You have to do the same procedure and write the equations for region 2. So for the region 2, the electric field again is in the x direction, here is also in the x direction. Understood? So we are taking x cap common, so you will left with incident and reflected. Incident e, we are denoted by E naught plus, the wave propagation in the positive z direction, that's why we are taking plus iota k2z minus iota omega t, as it is time dependent. Okay, for the case of reflecting back wave in region 2, it becomes E naught minus, and now the wave propagation direction changes into negative z direction, that's why we are using here minus iota k2z minus iota omega t as it is. Okay, now this is the electric field in region 2. Now you have to write the same procedure for the case of magnetic field in region 2. Again the magnetic field is common in the y direction in both incident and reflected in region 2, but incident is the positive y direction, and for the case of reflecting back this is in the negative y direction, okay, in region 2. So taking y cap common, so you will left with h naught. You know that h naught basically equals to E naught by z. Okay, because you are into the second region, so you have to use E naught plus divided by z2, because you are into second region. E naught plus for the case of incident wave in region 2, e power iota k2z plus iota omega t plus iota k2z, because your wave propagation is z in the positive z direction. Whereas your reflecting back wave concerned in the region 2, the direction of wave propagation now changes, inverses in the negative z direction, so that's why it becomes minus iota k2z. And your magnetic field is also in the negative y direction. Negative is here, y is already I taken as common, so it becomes E naught minus for the case of reverse back divided by z2, because you are into second medium, minus iota omega t as it is. So these are the equations in region 1 and region 2. Now you have to write same procedure for region 3, because there is no reflection back in region 3, only there is transmitted part. So how we can write the transmitted part? We can write our transmitted part et3. Okay, you can say E3 plus. So E3 means your electric field into the third region, your electric field direction is again in the x direction, that's why x by x cap common. Now E naught, which is the amplitude, because there is only going wave, so E naught plus, and the wave direction now in the positive direction, okay, positive z direction, so it becomes iota k3z. Now your z is changes into z minus d, because you can see here is the boundary z equals to 0, here is the boundary z equals to d, and when you are in this medium, so you have to whole is z and this is d, so you have to minus z minus d here. So instead of now writing z, you have to write z minus d for the case of region 3. So it becomes z minus z d instead of z minus iota omega t as it is, because there is no reflection back, so that's why this is empty. Again you have to write the same procedure for the magnetic field in region 3. You can write, because you know that magnetic field is again is in the y direction, and then in the positive y direction in region 3, and here is the amplitude, which is h naught, and h naught you know that E naught by z, because you are in third region, so that's why E naught plus divided by z3. e power iota k3. Now again your d changes into z minus d, because your total distance is z and here is the boundary d. Whenever you are in the third region, you have to minus d from the total, z minus d, it becomes minus iota omega t as it is. So these are basically the electric and magnetic field equations in region 1, 2 and 3. Now let's move on towards applying the boundary conditions. We have two boundary conditions at z equals to 0, and we have to apply the second boundary conditions we have at z equals to d. As you can see here, z equals to 0 and z equals to d. So let's first apply our first boundary conditions. Our first boundary condition is at z equals to 0. What we have to do here, just put the value of z equals to 0. If we need see that here is z, here is z in power of exponential. Always we can see z in every equation. You can see the power of exponential power, there is some z. So you can apply the boundary condition z equals to 0 only into first two regions, because this boundary condition is only applied in the first two regions, z equals to 0, you can see. So now let us apply the boundary condition z equals to 0 in this. Okay, so applying z equals to 0, you know that exponential term becomes now equals to 0, because in every part there is z, but in the exponential power, so exponential power 0 means 1. So you will only left with, and these amplitude constants cancels with the region 2 amplitude constants, and you will only left with E naught I plus E naught R for electric field equals to E naught plus E naught minus. This is equation A. And let's compare the magnetic field equations of region 1 and 2. So you can see again the directions and amplitude cancels with the other directions and amplitudes. You will only left with z1 cancels with the okay, so you can see that it left with E naught I. Okay, you can see this E naught I minus E naught R, and taking z1 common from in denominator and have to multiply to the other side. So you can see z1 divided by z2 from here, and E naught plus and E naught minus from here. So these are the equations after applying the boundary conditions. Now let's apply the boundary conditions z equals to d in region 2 and 3. You know that there is a boundary condition z equals to d in region 2 and 3. So let us apply this boundary condition in region 2 and 3 and have to equal, because we know that the tangential components of electric field E are equal or continuous, while you also know that the tangential components of magnetic field H are also equal and continuous. That's why we are doing and applying this boundary condition. If the tangential components are not equal, then we are supposed to not do this process. First of all, we have to convert. If we have B, then we are not gonna apply these rules on B. First of all, we have to convert B into H, then we have to apply, because we know that the tangential components of E and H are equal. That's why you can see E are equal, and you can tangential components of B are equal. Similarly, tangential components of E and tangential components of B, we have to post equal and apply the boundary condition at z equals to d. So you can see here like again you have, this is region 2 and 3. We only apply our second boundary condition z equals to d in region 2 and 3 only, because you can see the second boundary condition is only in region 2 and 3. So let us apply first in for the case of electric field. Again directions and amplitude got cancels with the other region. You will only left with, you can see E naught plus e power iota k2 okay, z becomes d, because z is equals to d is the boundary conditions, and e power iota omega t taking common from the region 2 and taking common from region 3 cancels each other. Okay, you will only left with E naught plus e power plus iota k2d plus E naught minus e power minus iota k2d. Okay, from this you have to equal with the same electric field in region 3. Again this direction and amplitude cancels with this, and e power minus iota omega t cancels by taking common in region 2. You will only left with e power iota k3 z minus d, but when you have to put z equals to d, so it becomes d minus d, means exponential power 0. Exponential power 0 becomes 1, so it becomes 1. So you will only left with E naught plus, means E naught t, you can say, transmitted part. Similarly, now I have to write the same thing for magnetic field of region 2 and 3 and apply the boundary condition as z equals to d. Again the directions and constants got cancels with other region direction constants. You will only left with E naught plus e power iota k2 d. Z becomes d, because z is d in the boundary conditions. again minus sign here, e naught minus e power minus iota k to d, okay, equals to, by taking z2 common in the denominator from this equation, have to multiply that z2 to the other side of this, and it becomes z2 by z3. You can see z2 by z3 and e naught plus, and here when you apply boundary condition d, so d minus d becomes 0, exponential power 0 becomes 1, so that's why you will only left with z2 by z3 e naught t. So these are the boundary conditions after applying. So let's move on towards further to find our conclusion for the finding the transmission and reflection coefficient. As you see that these equations are so called as A and this is B, and you have to say this equation as C and this equation as D. Now let's proceed our derivation. Now what we are going to do here, now we divide equations C and D by e power iota k to d. This is our equation C and D as you see previously. Now what you have to do, just divide your equation C and D by e power iota k to d. After dividing, you will only left with this. This is your C equation, e naught plus e naught minus e power minus iota k to d equals to e naught t e power minus iota k to d. You will only left with this equation. This is your modified C equation after dividing by this e power iota k to d, and below is the modified D equation. After when you divide your D equations by this e power iota k to d, you will left with this e naught plus minus e naught minus e power minus iota k to d equals to z2 by z3 e naught t e power minus iota k to d. What is cancelling here? You can see e naught plus e naught plus. Now what you have to do here, firstly you have to subtract these equations. By subtracting, you can change the signs below. So e naught plus cancels with e naught plus, and e naught minus plus e naught minus becomes 2 e naught minus. This is taking common e power minus iota k to d, and you have to add e power minus iota k to d is common, and e naught t is common. What is left? 1 minus z2 by z3. Okay, because our task is to first find e naught minus, means reflected back electric field, and then we are going to find e naught plus. So we when e naught minus, we have to move this 2 and this exponential to the other sides. Exponential goes to other sides, and there is also an exponential terms. So this is minus 2 here, here is 2 minus 1, so it becomes iota k to d, and e naught is as it is, and this 2 divides to the other side, and after taking LCM of this, you will get e naught minus, which is equals to z3 minus z2 divided by 2z3 multiplies by e naught t e power iota k to d. Okay, so let's say this equation as equation I. Okay, now move towards further. Now similarly what you have to do, as we did above, like we divide our equation C and D by e power plus iota k to d. Now you have to do the same scenario, but here you have to divide your equation C and D by minus iota k to d. Okay, e power minus iota k to d. So you will left with this. You can see e plus e power plus 2 iota k to d plus e naught minus equals to e naught t e power iota k to d. Okay, similarly when this is the modified equation C after dividing by e power minus iota k to d, and this is your modified equation D after when you divide your equation D by e power minus iota t k to d. So you can see now after dividing this, you have to add. After adding, you can see e naught, now e naught minus cancels with e naught minus. Initially you can see e naught plus cancels with e naught plus, and you have to find e naught minus. Now you can see e naught minus would be cancelled, and you can easily find e naught plus because you can see e naught plus add with e naught plus, left with 2 e naught plus, and e to the power plus 2 iota k to d common. Okay, similarly here e to t is common, e power iota k to d is again common. You will left with 1 plus z2 by z3. Understood? So you can easily find e naught plus from here by moving this 2 to the other side, divide, and taking LCM of this, you will left with e naught plus, and that is equals to z3 plus z2 divided by 2z3 multiplies by e naught t e power minus iota k to d. So this is how you can find the e naught plus and e naught minus. Why we found this? Because we have to use this e naught minus and e naught plus in our further relations to find our transmission and reflection coefficient. So that's very useful. That's why we found that. Now move on towards next. Now what we are going to do now we are adding our equation a and b. You already know what are our equations a and b. A and B are the equations you know that we found by applying the first boundary conditions. After applying the first boundary condition at z equals to 0, we have two equations of one is electric field, one is the magnetic field. So that equations are a and b. Now what we are doing, we are just adding our equation a and b. So these are our equations. You see, we are just adding. So e naught r cancels with e naught r. You will only left with e naught I. So when it adds, e naught I plus e naught I becomes 2 e naught I, and here e naught plus take common. You will only left with 1 plus z1 plus z2. Again here is e naught minus is common, 1 and minus, because minus is here, 1 minus z1 by z2 for the case of z1 minus, because we need the incident electric field. So what we are going to do, we have to divide this 2 to the other side, and taking the LCM of these relations, you will only left with the incident electric field E naught I is now equals to Z2 plus Z1 divided by 2 Z2 E naught plus Z2 minus Z1 divided by 2 Z2 multiplies by E naught minus. So now you can see in the relation of incident electric field there is E naught plus and E naught minus. Now we can easily substitute these E naught plus and this E naught minus in our this relation to finally easily find the incident electric field. Okay, now let's move further. We already find our incident electric field relation in term of E naught plus and E naught minus. Just leave that equation till now, and let's now again subtract our equation A and B. As before we did only add our equation A and B and find E naught I. Now let's assume and subtract our equation A and B. After subtracting, now your incident term got cancelled, and you will term E naught plus E naught plus becomes 2 E naught R. Okay, and here you can see E naught plus is taking common. You will left with 1 minus Z1 minus Z2, Z1 by Z2. Again here is E naught minus is common, and here is minus, and the here is minus, minus becomes plus. So you will left with 1 plus Z1 plus Z2 for the case of E naught minus when taking common, because we need the E naught R reflected electric field. We have to move this 2 to the other side, and taking the LCMs of these factors, we will left with E naught R, and our E naught R reflected electric field basically equals to Z2 minus Z1 divided by 2 Z2 multiplies by E naught plus Z2 plus 1 Z1 divided by 2 Z2 multiplies by E naught minus. So this is my electric field reflected for the case of reflection, for the case of electric field in term of E naught and E minus. So we successfully find our incident electric field in term of E naught and E plus, and we successfully find the reflected electric field in term of E naught and E plus. Now we can easily substitute the values of E naught plus and E naught minus in these equations. So for that, first of all, let's first substitute the value of E naught minus and E naught plus in equation 3. This is equation 3. You know that this is our equation 3 of incident electric field in term of E naught and EI. Just put the value of E naught plus and E naught minus here, which is these values, E naught plus and E naught minus. So let's just put these values. So you can see I just put it. This is E naught I, and this is the value already, and this is the value I put E naught plus, and this is the value in formula, and this is the value of E naught minus. Okay, now what you have to do, see here, E naught T is common in both these. Just take E naught T common, and there is 2 here, means 4 in the denominator. In here also 2 multiplies by 2. In denominator again there is 4, so 4 is also common from the denominator. So you will only left with Z2 plus Z1 multiplies by Z3 plus Z2. Similarly, left with e power minus iota k to d. Here you will left with z2 minus z1 multiplied by z3 minus z2, and e power plus iota k to d is common, divided by z2 z3 z2 z3. Understood? And here you can say e power plus iota k to d. Now what we are going to do next, we have to take LCM. You can see z2 z3 z2 z3 is common in both denominator. Just take common and you can see this equation as, let's suppose, and write this equation as equation 5. And you can see this is your equation of incident electric field in term of transmitted electric field. So you can easily find the transmission coefficient by using this equation 5. Keep remember this equation, we will find the transmission coefficient in few times ago. After some time we have to use this equation to find the transmission coefficients. So for that, just wait for that. And now let's move on towards putting your value of E naught plus and E naught minus in equation 6. This is your equation 6 for the reflected electric field. So you can see we are substituting z2 minus z1 divided by 2. Z2 is as it is, and this is E naught plus we have to put. So this is the value of E naught plus. Okay, similarly this is as it is, and E naught minus value is this. Here I substituted. Now again here is E naught t and here is E naught t common, and in denominator 2 multiplied by 2 4, 2 multiplied by 2 4, and we have to take common from the denominator. So E naught t divided by 4 is common, so you will only left when you have to multiply this by this and z2 multiplied by z3 in denominator. Similarly e power minus iota k to d as it is, and z2 plus z1 multiplied by z3 minus z2 divided by z2 minus multiplied by z3 is in the denominator. Here also e power plus iota k to d. What's next? You can see here in denominator z2 z3 z2 z3 is common. You have to take LCM. After taking LCM, you can see this is your relation of reflected electric field in term of transmitted, okay, electric field. Now what we are going to do next, our final part is focused only on to find the reflection and transmission coefficient. We can easily find the transmission coefficient by this equation, but how we can find the reflection coefficient? Because reflection coefficient, you know, that is basically the ratio of E naught R divided by E naught I. So E naught R is here and E naught I is here. Just divide both these equations, you will get your reflection coefficient. Quite easy. But how you can find the transmitted coefficient? By using only a single equation, equation number 5, because you know that your transmission coefficient is basically equals to E naught t divided by E naught I. So just move this E naught I in denominator of E naught t and move all other these values to the other side, and you will get your transmission coefficient. Okay, so now let's check it out how we can find this and how we can do so. So whereas your transmission coefficient concerned, as I told you that you have to use equation number 5. This is your equation number 5. Again I wrote here. Again you can see because we are going to find the transmission coefficient, because we need the ratio of E naught t divided by E naught I. Just move this E naught I in denominator of E naught t, multiply 4 z2 z3 above to the other side, and this divides in denominator to the other side. Okay, so this is the transmission coefficient of electromagnetic field in 3 regions which we initialize our problem. Okay, from where we initialize our problem. To check, to verify, we also solve the transmission coefficient in region 2. Means we have, when we have 2 regions, we already solved that problem in our previous lectures. If you forgot to watch, first watch that video, then move on towards this video. So to confirm, to verify our answer is correct or not, we are using some tricks. And here what we are going to do, we just have to verify our equations if this is equals when we are dealing with 2 regions. Also if the answers are both are same, whenever we are dealing with 2 regions or 3 regions, the only difference is just you have to apply, put d equals to 0. means whenever your d equals to 0 means exponential power. Here is d is always there in the power of exponential. So exponential becomes 0, and you know that exponential 0 is always equals to 1. So exponential terms vanishes. Now you can easily multiply z2 this both, z1 with these two, again z2 multiply by this both, and z1 again multiply z2 multiply by these both, and z1 multiplies by these both. After multiplying, sum of terms got cancelled, and you will only left with 4z2 z3 divided by 2z2 z3 plus 2z1 z2. Again in denominator you have to take common 2, and upside is 4, so 2 cancels with that 4. 2 1s are 2, 2 2s are 4. You will only left with here is z2 you can take common, and in denominator you can also take z2 common, because here is z2, here is z2. That z2 common cancels with the numerator z2, and you will only left with 2z3 divided by z3 plus z1, which is the transmission coefficient. Understood? Now let's find the reflection coefficient. As I told you that reflection coefficients can be found by just dividing your reflected electric field by the incident electric field. We already have both the equations. This is our reflected electric field, this is our incident electric field. Understood? Now what we are going to do here, just have to divide this both equations. You can see when we put this equation in numerator, this in denominator, you can see this z2 z3 cancels with this z2 z3, this e naught t divided by 4 cancels with this e naught t divided by 4. You will only left with this part in numerator and this part in the denominator when you divide e naught r divided by e naught I to find the reflection coefficient. Okay, so here is the which I told you. This is our reflected electric field equation, and this is our incident. When you divide, you can see this full term cancels with this because both are same. You will only left with this. So this is the equation, means you can say this is the reflection coefficient of electromagnetic field and waves in when we are dealing with three regions, region 1, 2 and 3. Okay, in the start of the lecture you see that there are three regions which we are concerned and solving the problem. So this is the reflection coefficient of that electric field. Again, as we check our transmission coefficient by putting d equals to 0, we can also check at d equals to 0 for reflection coefficient also, to check that whether we are dealing with two regions or whenever we are dealing with three regions, either the answer should be same at d equals to 0. So just we are going to do again e power, here is d, here is d, here is d, here is d. So exponential power d means exponential power 0 it becomes, and exponential power 0 you already know it's always equals to 1. So exponential terms vanishes all the way up, and you will only left with these z equations. What you are going now, just add these equations. Some of the equations cancels in the numerator and some of the also cancels into the denominator, and you will only left with this equation 2z2 z3 minus 2z1 z2. In the denominator 2z2 z3 plus 2z1 z2. What is common? 2 taking 2 common, 2 is 2 cancel. Again in numerator z2 is common, in denominator z2 is common. Taking z2 common, you will only left with z3 minus z1 divided by z3 plus z2. So here is you know that e naught by ei, which is the reflection coefficient. So your final reflection coefficient answer, and that is equals to z3 minus z1 divided by z3 plus z1. So this is how you can find the reflection coefficient of electromagnetic field equations. In this scenario we are concerning with the three regions, region 1, region 2 and region 3. Region 1 and 2 has a boundary at z equals to 0, and region 2 and 3 has a boundary condition at z equals to d. So solving that problem, you will get these relations. You can see this is our diagram, and these are our equations, and these are our final results. We are successfully finding our reflection and transmission coefficient. So this is our main reflection coefficient answer, and when we check, we verified that this is correct. And similarly, this is our final answer of the transmission coefficient in three regions, and when we successfully check that our answer is correct. So this is all about assignment number 2 of Advanced Electromagnetic Field and Waves. Thanks for watching. Stay tuned with us. Till then, Allah Hafiz.